Okay, in this video we're going to talk about an important theorem in calculus called Rolle's theorem. Rolle's theorem, named after Michael Rolle, who lived in the 16 and 1700s, a long time ago. Interesting character. I was just reading about him before I did this video. He was kind of a math hobbyist to begin with and got some jobs that allowed him to do mathematics more formally because of some things that he had solved. But the interesting thing about this guy, Michael Rolle, is he proved this theorem algebraically for polynomials only because he didn't buy into this new calculus idea. In fact, he tried many times to prove that it was fallible, that there were inconsistencies with it. Eventually, he came around to employ the techniques of calculus, but he was skeptic at first. Okay, so what is Rolle's theorem? Rolle's theorem is a precursor to something called the mean value theorem, which maybe is more well known than Rolle's theorem. But this theorem is a bit simpler to understand. So we're going to start with it. So Rolle's theorem says, suppose f satisfies the following three hypotheses. Okay, so when you remember Rolle's theorem, remember it has three hypotheses, three conditions that have to be satisfied. As we run through the conditions, I'll try to illustrate Rolle's theorem and go back and forth so we can fully understand it. So what we have is the first condition is the most basic hypothesis typically in calculus is that f is continuous on the closed interval from some a to some b. All right? So it has to be continuous on the closed interval. We have the further condition, which is also a popular hypothesis in calculus, that f be differentiable on the open interval. Okay? So continuous on the closed interval allows us to have endpoints that are closed and connected to the graph. Okay? The function being continuous means there's no gaps or breaks between a and b. The function being differentiable ensures that the graph is smooth. There's no herky-jerkiness to it, no sharp points. Okay? So what we see, if we were to illustrate this, is we'd have to draw a graph from A to B that is connected with no gaps or breaks and is smooth and is defined at the endpoints. So maybe something like this. No sharp points, no breaks. Very nice. Okay, so this function satisfies both of those hypotheses. Okay, so those are only two of the three hypotheses for Rolle's theorem. The third condition makes it somewhat specialized. So the third condition is we'll also assume that f of A equals f of B. In other words, the y value for A should equal the y value for B, and currently my graph here does not. So I will modify the graph to make that happen. So here's my y value for A. I'll link up my y value for B to be the same, and then I'll have the same sort of behavior here for my function in between. Okay. So this function satisfies the three hypotheses of Rolle's theorem. So we'll put a period here. So suppose that we have a function that satisfies all these hypotheses. What Rolle's theorem tells us in that case, it says, then there is a c, some number c, in the open interval from a to b. So this value of c can't equal a or b, it has to be between a and b. So Rolle's theorem guarantees that there is at least one c. There is one at least, there might be more. But there is a c in the open interval such that, and this is the interesting part, f prime of c equals 0. So let's think about what this means here. Here, we have a function f that satisfies all three hypotheses. And the idea here is that by requiring the y values at the beginning and the end to be the same, you can see that this line, which is called a secant line, that connects 2 points of a curve, so this is a secant line for this function, is horizontal. That's always going to be the case if f of a equals f of b. The secant line connecting the endpoints will always be horizontal, and that's kind of the key here. Because that's true, in addition to the smooth, continuous behavior of this function, we're guaranteed by Rolle's theorem that some number between a and b, at some number between a and b, we will have a derivative that equals 0, meaning we will have a tangent line slope of 0, meaning we will have a horizontal tangent line. And we can see, in fact, that this particular function has a horizontal tangent line there and another horizontal tangent line there. So in fact, for this particular function, we have two c values between a and b. Rolle's theorem guarantees one, there might be more, two c values for which f prime of that c value equals 0. So we could call this c sub 1 and this c sub 2. And if you were to look at f prime at c sub 1, that would be 0 because the slope of the tangent line at c sub 1 is 0. And f prime of c2 is also 0 because the slope of that tangent line is also 0. So Rolle's theorem guarantees this. And again, this condition that f of a equals f of b is a bit unique. And because f of a does equal f of b, we get this horizontal secant line, which guarantees that we will have at least one horizontal tangent line somewhere between those two values. Okay, so let's see if we can put this to practice so we can practice recalling the hypotheses and remembering the conclusion, right? So these hypotheses imply that this statement's true. Okay, so let's practice with this concept of Rolle's theorem. Remember, Rolle's theorem, three hypotheses. If you look at the mean value theorem, it's a bit more general. It only has two hypotheses, so that'll be a different video. But let's say we have this example. Show that this function f of x, which equals, I've got it written down here, the one I wanted to do, x cubed minus 9x plus 8. So we've got that function. Show that this function satisfies the hypotheses of Rolle's theorem on the interval -3 to 3. Okay? So what we're going to show is that this function satisfies all three hypotheses. And then, to finish the question, any function that satisfies those three hypotheses will allow us to employ Rolle's theorem and make the conclusion of the theorem. So once we know that this satisfies the hypotheses of Rolle's theorem, the next thing we want to do is then find all c values in the open interval that satisfy the conclusion of Rolle's theorem. Okay? So this is going to be an exercise in employing all the hypotheses in the conclusion of the theorem. You exercise theorems by practicing applying them lots of times, or you practice proving them. We're not going to do that here. But all right, so let's do the first part. Let's show that this function satisfies the hypotheses of Rolle's theorem on this interval. So the first hypothesis 1, if you will, says that f is continuous on the closed interval. F is continuous on the closed interval. Well, so we have to show that that's true. So this function f of x, so we could say this is a proof, but this function f is continuous on its domain because it's a polynomial. It's continuous on its domain, negative infinity to infinity, right? The domain of a polynomial is all real numbers. So this interval is bigger than this interval, thus f is continuous on the closed interval. No problem, right? F has to be continuous on that smaller subinterval. So that proves hypothesis 1, okay? Let's prove hypothesis 2. Let me switch colors here. That red's running out. So let's prove hypothesis 2, which states that f is differentiable on the open interval from negative 3 to 3. So we have to show that that's true. So if I want to show where f is differentiable, I better look at the derivative. So f prime of x equals 3x squared minus 9. Okay? 3x squared minus 9. And you can see that the derivative here is a polynomial also. So this derivative exists everywhere. You can calculate this value no matter what x is. There's no restrictions on this calculation. So f prime of x exists everywhere. Thus, f, since the derivative exists everywhere, we could say f is differentiable everywhere, or from negative infinity to infinity. Hence, we'll say it differently here. Hence, it is differentiable on the smaller interval, negative 3 to 3. So because the derivative exists everywhere, that means f is differentiable everywhere, which certainly means it's differentiable on the open interval from negative 3 to 3. So that shows hypothesis 2. Very good. Let's look at hypothesis 3. Hypothesis 3 states that f of a equals f of b. So in this case, f of negative 3 better equal f of positive 3. So this one's pretty easy to show. Let's look at f of negative 3. F of negative 3 is negative 3 cubed minus 9 times negative 3 plus 8. So we get negative 27 minus negative 27, which is plus 27, plus 8. Adding all that together, we get 8. F of 3 equals 3 cubed minus 9 times 3 plus 8. So we get 27 minus 27 plus 8. So we get 8 again. So we've proven that f of negative 3, therefore f of negative 3 equals f of positive 3. Let's make it very clear. Let's make our final statement here. Okay? So cool. This particular polynomial function satisfies all three hypotheses of Rolle's theorem. So we've got the first part of the problem done. Now the next part, it says find all C that satisfy the conclusion of Rolle's theorem. So let's remind ourselves of the conclusion of Rolle's theorem. We know that since this function satisfies the three hypotheses, we know for sure that there is a C that satisfies the conclusion. There has to be. That's what Rolle's theorem is useful for. So just to remind ourselves of the conclusion, it says there exist. Here's a symbol for there exist. It's a backwards capital E. There exists a C in the open interval from negative 3 to 3 such that f prime of C equals 0. We're guaranteed that that's true. Okay? So we just have to figure out all the C values that satisfy this condition. Okay? So if we want to figure this out, we need to look at f prime of x. Let's look at the derivative. Again, that's 3x squared minus 9. And what we want to do here is we need to know where does the derivative equal 0, right? Where does f prime of x equal 0? That's what we need to figure out. And the x values we get will be what we would choose for our c. Okay? So let's check it out. So 3x squared minus 9 equals 0, right? That's the derivative equals 0. We're going to solve for x now. So add 9 and divide by 3. So x squared would equal 3. And if we take the square root of both sides, we get plus or minus the square root of 3. Okay? Now, we're looking for any c values or any x values that are between negative 3 and positive 3, and both of these are. So the two c values, let's write it this way. C equals negative square root of 3, and c equals the positive square root of 3 satisfy Rolle's theorem. Now, if one of these was outside of this open interval, we would not put it in our answer because Rolle's theorem says that there exist c values in this interval. And so all we're doing is finding the c values that are in this interval to satisfy this condition. So that's a direct application of practicing with all the hypotheses and the conclusion of Rolle's theorem. Okay? Now, that was a polynomial which is continuous everywhere and differentiable everywhere. If you get a function that has a fraction or a square root, those are not defined everywhere all the time. So you have to remember your concept of domain to figure out where a function is continuous and differentiable. So keep that in mind. I can't possibly do examples of all those cases here, but I'm assuming you have the algebra background to recognize where functions are defined or are not defined. So that's kind of key there. You may encounter trig functions too, and you'll have to know where trig functions are and are not defined. Okay? All right, let's do another example with Rolle's theorem, but let's put a different spin on it. So show that when, let's phrase it differently. Show that f of negative 1 equals f of positive 1 when f of x equals 1 over x squared. Okay? So we're going to show that that's true. You might recognize this as being something similar to the third hypothesis of Rolle's theorem. And by the way, you don't have to remember the hypotheses in that order. You just have to remember the three hypotheses. Okay? So we're going to show that f of negative 1 equals f of 1 for this particular function. Okay? But then what we're going to do, then show that there is not a c in the open interval from negative 1 to 1 where f prime of c equals 0. So that'll be interesting because Rolle's theorem guarantees that there is a c in the open interval where the derivative equals 0. And for some reason, here there's not. Okay? And so what we want to do is explain. So we're going to show that there's not, and then we'll explain why this doesn't contradict Rolle's theorem. Because if we found a contradiction to Rolle's theorem, that would mean that Rolle's theorem is not true. But it should be. It's a theorem, right? So here we go. Let's do the first part. Let's show that f of negative 1 equals 1. Let's show that. F of negative 1 equals f of 1, I think. I think I said that wrong. So f of negative 1 equals 1 over negative 1 squared, right? Just plug negative 1 in. So you get 1 divided by 1, which is 1. f of positive 1 equals 1 over 1 squared, which is 1 over 1, which is also 1. Therefore, f of negative 1 equals f of 1. Okay, that's good. We've shown the first part of the problem. Okay, but now we're going to show that in this open interval, we can't find any numbers for which the derivative of the function equals 0. Okay, so let's consider f prime. Let's consider f prime of x. Okay, consider f prime of x. Well, f of x, the easiest way to differentiate 1 over x squared is to rethink of it as x to the negative second power. 1 over x squared is x to the negative second power. So f prime of x, we can just use the power rule and get negative 2x to the negative third power, right? When you lower negative 2 by 1, you get negative 3. And then rewriting this again, it's the same thing as negative 2 over x to the positive third power. Okay? So what we want to do is we want to find where the derivative equals 0. We want to find where the derivative equals 0, and any answers we get should not live within this open interval. Okay? So we want to find where f prime of x equals 0. So we need to solve the equation negative 2 over x cubed equals 0. And you may already see that this is impossible. You can't take negative 2 divided by anything and get 0. But if you don't see that and you proceed to do the algebra, what you would do at this point is you would take and you would multiply both sides by x cubed to cancel the denominator on the left side. And you would get negative 2 equals 0 times x cubed is just 0, which is impossible, right? So there's no way that this equation can be true. So there is no solution. There is no solution to the equation negative 2 over x cubed equals 0. That's the same thing as f prime of x. So f prime of x does not equal 0, ever. So for any value of x, f prime of x does not equal 0 for any value of x. So that means there's no c that we could plug in for x. No c will satisfy that equation. Okay? So we've shown that there's not a c in this interval. In fact, there's not a c in any interval that will make the derivative of this function equal 0. Now, Rolle's theorem guarantees that there is a c that would make the derivative equal 0. So the last part of the question is to explain why we did not satisfy Rolle's theorem. What was the problem here? Okay, so let's address that. When can we make the conclusion of Rolle's theorem? Think about that. When are we guaranteed that there is a c where the derivative equals 0? Well, we're guaranteed that when we satisfy all three hypotheses of Rolle's theorem. And in this particular problem, we've only satisfied this one. Okay? So let's consider f of x equals 1 over x squared. So we are not contradicting Rolle's theorem. We are not contradicting Rolle's theorem, since this function is not continuous everywhere. It's not continuous if x is 0, right? F of x equals 1 over x squared is not continuous at 0, right? And for Rolle's theorem, the function has to be continuous on the closed interval from, in this case, negative 1 to 1. 0 lives between negative 1 and 1. So thus, f is not continuous on the closed interval from negative 1 to 1. because it's not continuous at 0, which lives in this interval. And if f is not continuous on the closed interval, that's one of the hypotheses of Rolle's theorem. So f fails this hypothesis of Rolle's theorem. And once you don't meet one of the hypotheses of a theorem, you have no guarantees anymore. Okay? So sometimes when you do a problem like this, your function might be continuous on the interval. Okay? That could happen. But you've got another hypothesis as well. The function has to be differentiable on the open interval. So you may have to look at your derivative and see that it's not differentiable on the open interval. And in that case, you're not contradicting Rolle's theorem either. Okay, so we looked at Rolle's theorem, we stated it, we understood it with a picture. Then we did an example applying directly the three hypotheses and the conclusion of Rolle's theorem just to really understand it. And then we worked through it a little bit differently, showing an example of a function where f of a does equal f of b, but this function did not satisfy the conclusion of Rolle's theorem because it actually fails one of the three hypotheses.